Hello viewers, in today's class we are going to discuss yet another very important application of Lagrange's mean value theorem, right? So here we'll utilize Lagrange's mean value theorem in proving this given important inequality, right? So here before solving this inequality, let us quickly see the definition or the statement of Lagrange's mean value theorem, right? So viewers, in differential calculus, Lagrange's mean value theorem of it plays a very vital role, right? And it has wide applications. So here we'll prove this inequality, that is mod of sine alpha minus sine beta is less than or equal to mod of alpha minus beta for all alpha beta belonging to the set of real numbers, right? So let us take the advantage of Lagrange's mean value theorem to prove this inequality. Now we know that suppose we have a function, say y is equal to f of x, which is defined in some domain D, and let us take an interval that is a comma b, which is a subset of this domain D, right? So here x is the independent variable and y is the dependent variable. Then if we have the conditions that f of x is a continuous function in the interval a comma b, right? So here we have the closed interval, right? And if f of x is a differentiable function, or it is derivable in the open interval a comma b, then Lagrange's mean value theorem says that if a function y is equal to f of x, if it satisfies these two conditions, then there must exist some point in this open interval, say the point is x is equal to c, right? Then c, it belongs to this interval a comma b. This is the open interval, so we can also write it as c greater than a and less than b, right? So then there must exist a point x is equal to c, such that the derivative of this function, because this function is already differentiable, right? So the derivative of this function at this point, which can be written as f prime of c, then f prime of c must be equal to f of b minus f of a divided by b minus a, right? So this is the statement of Lagrange's mean value theorem, right? So now we'll apply this statement to prove this inequality, and we'll here assume an appropriate function, right? So to prove this inequality, let us assume that we have a function, say y is equal to f of x is equal to sine x, right? So here we'll take the function as sine x, and here we can take the interval, say alpha comma beta, right? Where alpha and beta, both numbers are real numbers, or they both belong to the set of real numbers, right? Now from trigonometry, it is quite evident that f of x, which is sine x, this is a continuous function in the interval alpha comma beta, right? Because we know that the sine function is a continuous function in the interval, or in any interval alpha comma beta, where alpha and beta belongs to the set of real numbers, right? Now let us find out the derivative of sine x. So f prime of x is cos x, because the derivative of sine x is cosine x. And again from trigonometry we know that cos x is derivable, or it is a differentiable function, right, in the interval alpha comma beta, right? So here this function f of x is equal to sine x, it satisfies both the conditions of Lagrange's mean value theorem. So sine x is a continuous function and it is also a differentiable function. So now the Lagrange's mean value theorem says that there must exist some point that is x is equal to c, uh, which belongs to this interval, that is a comma b. Here we have alpha comma beta, right? So c belongs to the interval alpha comma beta, right? Such that c is greater than alpha but it is less than beta, such that f prime of c is equal to f of beta minus f of alpha divided by beta minus alpha, right? Okay, now f prime of c can be obtained from this expression. So here we'll take x is equal to c. So now we can write cos of c is equal to f of beta. Now f of beta can be obtained from here by taking x is equal to beta. So we have sine of beta, then we have f of alpha. So we have sine of alpha by taking x is equal to alpha, and here we have beta minus alpha, right? So now we have obtained this important expression which can be utilized to arrive at this inequality, right? So now at this point, let us take the help of trigonometry, right? Now see, we know that the cosine function, it lies between minus 1 and 1, right? Because the range of cosine function is from minus 1 to 1, right? So this expression can also be written as that is mod of cos of c must be less than or equal to 1, right? So this is an important result in trigonometry. So mod of cosine c must be less than or equal to 1. So cos c is sine beta minus sine alpha over beta minus alpha. So let us substitute the value of cos c over here. So we have mod of sine beta minus sine alpha divided by beta minus alpha. This is the entire mod function, and here we have less than or equal to 1, right? So now here we'll make use of one important property of mod function, right? Now see, we know that mod of x over y is equal to mod of x divided by mod of y, right? And obviously y is not equal to 0, right? So mod of y is not equal to 0. So here if we apply this result, we'll get mod of sine beta minus mod of sine mod of sine beta minus sine alpha divided by mod of beta minus alpha, and here we have less than or equal to 1, right? Now here the denominator is the mod of beta minus alpha, and this is obviously not equal to 0, right? Because here we have a finite interval, so this quantity cannot be equal to 0. So now we can take it to this side. So we can now write mod of sine beta minus sine alpha is less than or equal to mod of beta minus alpha, right? And again we can use the property of mod function, that is mod of x minus y is equal to mod of y minus x, right? So here we can now write sine of alpha minus sine of beta, mod of sine alpha minus sine beta is less than or equal to mod of alpha minus beta, right? Which is the desired inequality, right? So viewers, this is how we can prove this inequality, right? Okay, now here we can also derive an important result from this inequality, right? See, if we take beta is equal to 0, right? Because 0 is a real number, and if we take beta is equal to 0 in this inequality, then we'll get mod of sine alpha minus sine beta is obviously sine 0, because here we are taking beta is equal to 0, so sine 0 is equal to 0, so we have mod of sine alpha minus 0 is less than or equal to mod of alpha minus 0, right? So this can be written as mod of sine alpha, that is less than or equal to mod of alpha, right? So we have an important inequality from this inequality, that is mod of sine alpha is less than or equal to mod of alpha, where alpha, it belongs to the set of real numbers, right? So viewers, this is how we can make use of Lagrange's mean value theorem to prove these type of inequalities.